Alright guys, just a couple more days and then we'll have the exam on Monday. We're going to get into friction today and we'll do at least one example, maybe two. So it'll be more like what you'll see in the exam. Two body problems where we'll work through at least one today. And then on Friday we can cover that. So also if you have any questions about the exam, we'll probably have some time on Friday so we can deal with that. So be thinking about that. But I'll also be around. I'm going to be out tomorrow afternoon, but I'll be around today and Friday. But I'll be around tomorrow morning as well. I'll get in at 8. All right. Morning. Let's see. We're going to be looking at friction quite a bit, and friction will sort of complicate things because friction is just another added force, and then also friction is dependent upon our normal force, as we'll see. So when we're dealing with either static or dynamic objects, that is stationary or moving objects, that friction will just make things a little more difficult. We can think about friction in two different scenarios. We can think of macroscopic friction and microscopic. Honestly, I'm not going to ask you about this on the test, but I just think it's kind of interesting. So if you want to write a note next to your notes, this is not on the test, but it's fairly interesting. Now, macroscopic, of course, means big, right? So when we think of macroscopic friction, it'll look like this. So if I have two surfaces that come together, and they have sort of rough crags on one another, and when they come together like this, they're going to experience friction, right? Just because they're catching on the other surface. So that would be what we call macroscopic friction. But in the lab, if you take these objects and you smooth them, very, very smooth, what's going to happen to the friction? It'll increase or decrease? It'll decrease, right? So as you make those surfaces smoother, you'll find that the frictional force will decrease, right? Because you're not actually catching onto the crags of the surface. But if you continue to make it smoother and smoother and smoother, eventually you'll get to a point where the frictional forces will actually begin to increase. Why is that? You make them so smooth that eventually the frictional forces begin to increase. And this would be where we move from macroscopic friction to microscopic friction.
More contact.
But you have more contact, and then literally your atoms in the material are beginning to bond with one another. So at some point, as you smooth these surfaces, so if I were to plot the frictional force versus the smoothness, your frictional force would be big originally, and then as you make it smoother and smoother, I'm not sure actually what the function is here, but it probably looks something like this. As you make it smoother and smoother, the frictional force decreases until at some point it begins to increase again. Now it never actually gets to the original frictional forces that you felt over here, which were quite large, because macroscopic friction can be quite a lot larger than microscopic. But at some point you begin to transition between macroscopic, which is just due to the physical crags of the material, to microscopic friction, which is due to the interactions between the atoms or molecules in the material. They get really close together, as Cole said. You have an expanded surface area as well. And then also the atoms are just interacting with one another. As I said, we won't see that on the exam. I just think it's kind of interesting. And y'all do too, right? Because you already say, gosh, that is kind of interesting that you have this different types of friction. We'll see that friction is always opposite the direction of motion, or it's opposite the force intending to cause motion. So it's opposite the direction of motion, or it's opposite the force intending to cause motion. Let me show you. Let's say that we have an object that is moving with a velocity in this direction. It sits on a certain surface. Then the frictional force, we're going to use the lowercase script f for the frictional force, will be opposite the direction of that motion. Right? That's for a moving object. But let's also say that we have an object that sits, say, on an inclined plane. Right, in this case, it's not moving. We'll say that it's just stationary there. But what will be the direction of the frictional force in this case? Would it be down the inclined plane or up the inclined plane? is going to be up the inclined plane, because this object would tend to move down. It has a force that's pulling it down, some component of the weight, and so the frictional force will be opposite that. So here, the frictional force is up the inclined plane, and as I said, you can think of it as being opposite the force, which in this case is the x component of the weight that is tending to cause the object to move. All right. We're going to talk about two types of friction. Static friction, it acts on objects that are stationary. And that'll be in contrast to kinetic friction, where we'll see acts on objects that are moving. Static friction is equal to, we're going to use the script F with a subscript S for static. It's actually not equal to, it is less than or equal to mu S times the normal force. Here mu S is the coefficient of static friction. Soon you guys will do a lab with the inclined plane. I think y'all haven't had your midterm yet in lab, have you? You have? Okay, well the very next lab that you'll do, I guess this week, will be, you'll actually determine what is the coefficient of friction. So what is the coefficient of static friction? There are no units to this. It's found experimentally by taking the ratio of the static frictional force over the normal force. So for a given object, you measure the static frictional force, you measure the normal force, and that gives you this coefficient of static friction. The coefficient of static friction is only dependent upon the type of material. So you have different materials that have different coefficients of static friction. So for example, rubber and ice have different coefficients of static friction. Which do you think has the bigger coefficient of static friction? Rubber or ice? Rubber, right? It has more friction because of just the type of material that it is. Or sandpaper versus glass, right? Sandpaper has a higher coefficient of static friction. It's also dependent not only on just the material, but the material that it's interacting with. So rubber on rubber has a certain coefficient of static friction, but rubber on wood would have a different coefficient of static friction. So in the tables that you find for coefficients of static friction on the internet or in various handbooks, they'll specify one material on another, what is that coefficient. Right? So it's only dependent upon the type of material. Right there. So this is dependent upon the material only. Dependent on the material. All right, so we notice that the static frictional force is dependent upon mu s. The static frictional force is also dependent upon the normal force. So for example, if I have an object, say this calculator, and I push it across this surface, it experiences a certain frictional force, right? Actually, the frictional force that this is experiencing is not static. Why is it not the static frictional force? Because it's moving, right? We'll see. This frictional force is very similar. It's called the kinetic frictional force. So that frictional force is governed by the two surfaces, the surface of the case here and the surface of the console. It's also determined by the normal force, which in this case is just what? Equal to what? The what? The weight, right. So the weight of the calculator is equal to the normal force because it's sitting on a horizontal surface and there are no other forces acting on it. It's pretty easy to move. However, if I push down on it, if I apply a force in the downward direction, what happens to the normal force? Does it increase, decrease, or stay the same? It increases. I'm adding another force. So it increases that normal force. If this is my calculator, it has the weight right here, the normal force right here, and then I'm applying a third force, F, and so that normal force is equal to F plus the weight. I'm adding a third force that increases the normal force. And if I do that, it also increases the frictional force. So then it becomes a lot more difficult. Like just by adding a little bit of force up top, it's very difficult to move the calculator. because I've increased that static frictional force by increasing the normal force. So the frictional force is dependent upon the material and then also on the normal force. Let's see, not a demo, well, I want to show y'all something. Actually, we'll come back to this in just a bit, and I'll show you in just a little bit. Now, kinetic friction acts on objects that are moving. And for almost all materials, or let's see, the kinetic friction, is equal to mu k times the normal force. Oh, and I forgot to show something, and that is, can I go back up? Forgot something I was going to say. There's something else important about this static friction that we've written here, and that is that this is not an equality, but instead it's an inequality. That is that the static friction is less than or equal to mu s times the normal force. So say, for example, you're trying to move an object. So I have an object here, and I'm pushing on it with a certain force, F, and I know then that the static frictional force, Fs, is in this direction, and my Fs is less than or equal to mu s times my normal force. I know that. That means that Fs can be arranged anywhere from 0 up to some maximum value. So if you imagine that this is the object that I'm pushing, so I'm applying a force in this direction, that means that the static frictional force is back the opposite direction. Right? If I push on in this direction, there's a static frictional force that's opposing that tendency to motion. Now, if I push on this with a force of, say, 5 newtons, what is the static frictional force? It's what? It has to be 5. Otherwise, if it's, say, more than 5 or less than 5, then my net force won't be 0, and it will be moving. So if I push on this with 5 newtons, then my static frictional force is also 5 newtons. If I push on it with 8 newtons, my static frictional force is what? It's the same, right? If I push on it with 10 newtons, the frictional force is 10 newtons. If I push on it with 20 newtons, it's 20 newtons, until I get up to some maximum value. Like say, for example, let's say that mu s is 0.1, and the normal force, that is the mu between the floor and this piece of furniture, is 0.1, and the normal force is, say, I don't know, 5,000 newtons. All right, that means that my static frictional force is less than or equal to 500 newtons. All right, that means that the static frictional force is going to range anywhere from 0 to 500. And then when I get to 500, it's not going to move. But when I get to, say, 500.1, what's going to happen to my furniture? It's going to move, right? So I have a couple of things about the static frictional force. It's dependent upon mu, which is the material, the strength of the material. It's dependent upon the normal force. If that increases, the frictional force increases. And it's also an inequality. That means that the static frictional force is not only dependent upon these things, it's also dependent upon the opposite forces. All right, and it's going to match those forces up until it gets to some value. And that's what this inequality means. We don't see that with kinetic friction, but we see it with static friction. Now, with kinetic friction, it's objects that are moving. This is an equality. It looks a lot the same. It's equal to our coefficient times my normal force, so all that still applies. Now, if you've ever had a material that you're trying to push, or like a big piece of furniture, I take this. Is that a smartwatch? Is that a smartwatch? I met a 9-year-old that had a smartwatch this weekend. So let's say that you have like a big piece of heavy furniture and you're trying to move it across the floor. What is it about moving that furniture after I get it moving? Is it easier to move it after I get it moving, or more difficult to move it after I get it moving? Or the same? It's easier, right? If you've ever moved like a big piece of furniture or a big box, you know that after you get it moving, it's a lot easier. And it's not because you've overcome the inertia or whatever. It's not because it's because of that. It's because for almost all materials, the kinetic
coefficient of friction is less than the static coefficient of friction. So that means, say, with my big couch or whatever, my big piece of furniture, these aren't wheels, they're like legs. After I get it moving, then it's a lot easier to keep it moving. So for furniture, for example, or a large box or whatever, it's a lot easier to move when it's in motion. That is, it takes a big force to start it in motion, but after you get it into motion, it's easier to keep it in motion. You follow me on this? It's because the kinetic friction is almost always less than the static friction. This comes up too in cars. A couple of things in cars that have to do with your brakes. When you leave today, if you're headed out up Maywood or wherever in your car, should have tried something a little different. So when you're driving along, and in your, I don't know, whatever your car, your Lamborghini or your Camaro or whatever, and you come to a stop sign, like instead of doing what you usually do, you just sort of fly right through the stop sign, like come to a complete stop. Have y'all ever done that? Come to a complete stop at a stop sign? Not a rolling stop, but a complete stop. What happens when you come to a complete stop? Right, you sort of lurch forward a little bit, right? The reason for that is well, what? What is the reason for that? Lurch forward. No. What is it? Inertia? Not inertia, no. I've already said it, right up here. What happens when you stop? Right, inside your wheel, you have a rotor, and you have these two brake pads that clamp down onto that rotor, right? You know what I'm talking about? And then as it moves, what type of friction is acting between the brake pad and the rotor? Oh, as the wheel is turning, it's connected, right? The rotor is actually moving with the relation to the brake pad. But then when it stops, it goes to static friction. So what happens there when you sort of lurch forward is you're transitioning from kinetic friction to static friction. And because there's a difference in those two forces, you sort of feel that jump in the car that is causing you to sort of jump forward. So try that as you head out today. Just as I said, you have to come to a complete stop, and usually you have to do it sort of slowly. But it's because of that difference in static and kinetic friction. That's pretty interesting, isn't it? Yeah, try it out today, or tell your friends to try it. There's another thing with cars, with the brakes in particular, that have to do with this difference between static and kinetic friction, and that's your anti-lock braking system. Now, if you've ever had like an old car, say from the 70s or maybe even like early 80s, you might have had a car like that or older. Okay, well, when you want to stop, especially on wet roads, what do? You pump the brakes, right? So when you want on these old cars, if you want to stop, especially on like really bad conditions, you don't slam on the brakes. Instead, you pump them. Right? Not even in bad conditions, but like if you're going fast and want to make a quick stop, you pump the brakes. And you do that. Why do you do that? Why do you pump the brakes? You don't have to. The reason you do that is so that your wheels don't lock up. Right? And anti-lock braking systems do the same thing, except it doesn't require you to pump the brakes. So when you step on the brake in your car, there are these actuators on your brake pads, and they clamp down and then they release. Clamp down and release. So they pump the brakes for you, basically. So these brake pads are going like this, just very subtly, but they're stopping, letting go, stopping, letting go, stopping, letting go, so that your wheels never lock up, no matter how hard you push on the brake pedal. All right? I think maybe if you slam on them hard enough, it will. All right, y'all should try that. So also when you're leaving on Maywood, if you start out here, maybe at Paltry, you can get up to about 50 or 60 miles an hour to the stop sign, and then just slam the brakes and see what happens. I don't do that.
Doing it for science.
What's that? Yeah. One of my students got a ticket. But anyway, so anti-lock braking systems are to keep your wheels from locking up. And why would you not want your wheels to lock up? Because you're sliding, right? So, and a sliding car is a lot more difficult to stop than a car where the wheels are not locked up. When you have a wheel that's turning, what kind of friction is at play there? Between the tire and the road. You'd think kinetic, wouldn't you? Because it's moving. But right, yeah. So as that wheel is turning, imagine this is the surface of the tire. As that tire is turning, it's not moving with respect to the road. It's not unless the wheel actually locks up and the wheel stops turning, does that tire begin to slide across the road. So when your wheels lock up, that's going to be kinetic friction, and when your wheels are turning, that's static friction. Now let's put this in words. So a couple of things here. One is that lurch that you feel at a complete stop. I don't know, is lurch a word? I'm just going to put it in quotes, and then it can be a word, right? If you put it in quotes, it's okay. So a lurch when you come to a complete stop. That's an A. All right, and this is due to the transition going from mu k, or the kinetic friction, to mu s. And because there's a discontinuity between those two, you feel that sort of lurch forward. And the second one is anti-lock braking systems. Keep the wheels from locking up. All right, and that's because a wheel that's turning, this is your tire, a tire that's turning with respect to the road feels a force that is my static friction, but a tire that is not turning, the force at play is the kinetic friction. And since Fs is greater than Fk, you want your wheels to always turn. All right, because that gives you a greater friction on the road. Okay. Let's work through a very simple problem, and then we'll look at some more complicated problems. I'm sorry, if I got that. Can I move down from here? Good. I'll wait just a second. All right, guys, you'll want to be looking, hopefully you've already done all of Chapter 3 homework, all right, and then you also want to now look at be looking at Chapter 4 homework. If you need some extra problems to work, let me know. Of course, you can look at the old test in that OpenStax book, which is on the course website. There's a lot of great projectile motion examples as well that are similar to things that we've done. So you can look at that as well. All right, let's look at this. This is a very simple problem, but just to start out, here I have a block that has a mass of 1 kilogram, and the coefficient of static friction between the block and the surface of the table is 0.1. And I just want to know what is the maximum force F here that I can apply so that the block still remains stationary. All right, so here all the forces are already labeled and identified. I'm going to draw them on a coordinate system. So there's my XY coordinate system. Here's my forces. This is my normal force. This is my force F. This is the force I want to know. This is my force Fs. And this is my F weight. Then there are no forces to resolve, so step 3 just goes away, and I skip right to step 4, which is I apply Newton's second law. Some of the forces in the x direction equals max. Some of the forces in the y direction equals may. Some of the forces in the x, that's going to be F minus Fs. The acceleration here, this is a statics problem, it's not moving, so that's equal to 0. Similarly here, Fn minus Fw equals may, but ay is equal to 0. So this is going to equal 0. All right. I also know over here that Fw equals m times g. M was 1 kilogram, so that's going to be 1 times 10, or 10 newtons. So now I look and see what it is that I want to know and what it is that I know. Let's see, I want to know Fs, and I don't know what the normal force is, or excuse me, I don't know Fs. I also don't know F, and I don't know Fn, but I do know the force weight. Alright. I also know that the static frictional force is equal to mu s times my normal force. So if I can find my normal force, I can find my static frictional force, and then I can find my force here. Alright, so solving these two equations, I have F is equal to Fs, and Fn is equal to Fw. Fn then is equal to 10 newtons. Alright, then I can take this, and I find that Fs is equal to 0.1 is equal to 1 newton. So that means that F is equal to 1 newton. And then that's the final answer. So the maximum force that you can apply there is 1 newton. Now hopefully, you might not be able to do this now, but hopefully you can just look at this and be able to intuit the answer, or be able to find the answer without having to go through this whole procedure of writing out Newton's second law and writing all the vectors and all that business. It might not quite be there yet. But when you're dealing with more complicated problems, you'll want to go through all those steps because they can be quite a bit more difficult. Alright, let's do one of those. Can I go down from here? Y'all have any questions about this? Feel okay about this? This was pretty simple, but your test isn't going to be like this. So here, I have two blocks. Both are stationary, and block B has a weight of 20 newtons, and the angle theta is 30 degrees. So they're connected by this system of rods. We consider them massless rods, or ropes if you want, but they don't bend, so they're not really like ropes. But I have an angle here of 30 degrees. I have a weight here of 20 newtons. So let's see, I'll start writing this over here. FWB equals 20 newtons. FWA, I don't know, but I want to know. I ask, what is the maximum weight of block A such that this remains at rest? And I know that the coefficient of static friction, mu s, for block B is equal to 0.2. Alright, first thing you want to do is to identify all the forces that are acting. And here we have a couple different forces, or a couple different bodies that we'll consider. The easiest way on this problem, actually, is to consider 2 points. We'll consider a point here, and we'll draw a vector diagram, or a free body diagram, for all the forces that are acting at that point. And then we'll also consider a point right here, and draw all the forces that are acting at that point. Why don't you go ahead and start that on your own. Draw all the forces that are acting at those 2 points. In just a second, I'll start with the red side, the red dot on block B. What I'm going to get then will be a system of 4 equations, and I'll be able to solve those in some way to find the maximum weight of block A. Alright, so on the block B, I have 4 forces. What are they? Okay, so I have Fn, and then I have Fw. I'm going to label it actually as FWB, so as to differentiate it between FWA. And then I have this is Fs. That's my static frictional force. because this block is going to tend to move to the right because of the force tension. And what did you call this, Michael?
I just call it.
Okay, I'm going to call it FT because it's a tension in the rope. And in fact, I'm going to call it FT1 because there will be a second tension that will be at play. All right, so that's my first one. And then what are the forces that are at work on this second point? How many forces are there, first of all? How many? At this point right here. Not two. How many forces? There are 3 forces, right? Is that what you said, Courtney? So, yeah, so there's a tension that pulls up in this direction. I'm going to call this FT2. There's a tension in this direction. Now, what is this tension? How is it related to the tension on the other block, FT1? Is it related? It's the same. So anytime that I have a rope and I pull on it in one direction and I pull on it on the other direction, then the tension in that rope is going to be the same throughout. So this force is going to be FT1, and then I have another force here, FWA. So I have 3 forces at work there. I'm going to draw the vector diagram and resolve the forces on the blue. So this is FT1. Here I have FT2. Was it cosine or sine? All right, the sine of 30. FT1 cosine of 30. And then FWA. Alright, so that I've resolved my vectors. That's that step 3 where I've resolved them into their components. I'm not going to do that over here for the red because they're already resolved. I can just draw my axes there. Alright, so that's that step. And now I want to write the equations for Newton's second law. I'll do it for the red first. So in all these cases, the acceleration is equal to 0. So in all these cases, the sum of the forces will equal 0. So I can do the sum of the forces in the y direction. That's Fn minus FWP. And then the sum of the forces in the x direction. That is Ft1 minus Fs. Both of these are going to equal 0. I can do the same for the blue. The sum of the forces in the y. I'll give y'all just a minute. So write the same for the sum of the forces in the y. I'll catch up with you in just a second. We're going to have a whole chapter on this, by the way, at the end of the semester while we're dealing with this in more detail, static problems. All right, so the sum of forces in the y, what is that going to be? I have Ft2 sine of 30 minus FWA. That's equal to 0. And sum of the forces in the x is Ft1 cosine of 30. Oh, yeah, I'm getting mixed up here. Ft2 cosine 30, excuse me, this should be a 2 up here. Minus Ft1 equals 0. Alright, so those are my values. Now I have a bunch of different unknowns in this, but I know some of the values. Like for example, I know that FWB is equal to 20 newtons. And because of that, I can also say that Fn is equal to what? I can say that Fn is also 20 newtons. I don't know what Fs is, but I know that Fs is equal to mu s times my normal force. So I can find this Fs right here, because now I know what the normal force is. Let me write this out a little more rigorously. So from this first one, this first equation, I can say that the normal force equals FWB, which is equal to 20 newtons. From this second equation, I can say that Ft1 is equal to Fs which is equal to mu s times the normal force. So Ft1 then is equal to 0.2, which is given, times the normal force, which is 20 newtons. Or what's that? 0.4? Yeah, 2/10 of 20 is 4. Alright, so I can find that Ft1. Now if I look in the second set of equations, let's see what I have as unknowns. I have Ft2, I don't know what that is, and I also have Fwa, I don't know what that is. And then similarly here I have Ft2, and I know what Ft1 is. So now I can solve this and find out what is my Fwa, which is really what I want to find. What is the maximum weight of that block that I can find where it won't cause block B to move? Okay, y'all with me on this? Once you get up to the equations, it's really just trying to find the appropriate way to deal with that system of equations in order to solve what it is that you want to find. Alright, so here I can first use this to solve for Ft2. So I find that Ft2 equals Ft1 divided by cosine of 30. I know Ft1 now, that's 4 newtons. Over cosine of 30, which works out to be 4.6 newtons. Alright, so that's my Ft2, and now I can come up here and solve this for Fwa, which is equal to Ft2 sine 30, or 4.6 times a half, which is equal to 2.3 newtons. And then that's the answer, that the weight of that second block, A, has to be no more than 2.3 newtons. Alright, in this problem, you see there's an opportunity for extra credit, and I'll provide the same for you, where if you solve the system of equations by a matrix, by inversion of a matrix, then I'll give you 3 extra points. Otherwise, you're not required to know how to do it. It says you only get to this like in Calc 3. But also, if you take linear algebra here, that's Alfred, right? Linear algebra? If you take linear algebra, which is an excellent course, by the way, like if you're intending to go to graduate school, I would highly recommend it. Because you deal a lot with dealing with matrices and solving systems of equations. So apparently you do that in Calc 3 as well. A little bit. But as an undergrad, like I found it to be one of the most useful classes I've had. So anyway, you can solve the system of equations in a slightly more convoluted way, but in a way that allows you to expand it to greater numbers of systems of greater number of equations. I'm going to write my 2 equations up here. These 2 equations right here in a slightly different way. Let's see, I have sine of 30 times Ft2 minus Fwa equals 0, and then cosine 30 Ft2 plus 0 times Fwa equals 4. Because I know that Ft1 is equal to 4, so I just brought it over to the right-hand side. So I've written these equations in this way so that I have my Ft2s all in one column, and then my FWA's all in one column. Now in the second equation there was no FWA, so I just put in a placeholder with a 0 right there. And then I can write this equation as a matrix where I have 0.5, -1, 0.86, 0, 0, and 4. It's called, anybody know what kind of matrix this is? What's it called? Starts with an A, do you know? It's called an augmented matrix. That means that I have this extra little thing off to the side of it. Now, if I can get this matrix into this form, in what we call an identity matrix, where it's 1, 0, 0, 1, then the numbers that I have over here on the right-hand side will be the answers to what is FT2 and what is FWA. So whatever number I have here will be the value for FT2, and whatever I have here will be the value for FWA. If you think about it, the way I've written these equations, it would be like saying 1 FT2 minus 0 FWA is equal to some value, and that value will be FT2. So we can go through this sort of system of maneuvers where we take this matrix, this 0.5, -1, 0.86, 0, and turn it into this matrix, a 1, 0, 0, 1. I call this an identity matrix. Let's see if I can remember all the rules. It's sort of like Sudoku. Y'all ever play Sudoku? This is a lot like that. It's like a little puzzle, and you have to get this matrix into that form. I think I wrote down the rules somewhere. Nope, guess not. All right, you can multiply any row by a scalar or by a number. You can replace any row with the sum of that row and another. I'll show you what this means in just a second. So, for example, I can multiply the first row by 2, and instead of 0.5, -1, 0, it will become 1, -2, 0. Multiply every number by 2. And then I could replace any row with the sum of that row plus another row. I'll show you what that means in just a second as we go through. Let's see, there's some other one. Oh, and then you can switch the positions of rows. All right, so I could move row 2 to row 1 or move row 1 to row 2. I know this seems really boring, but it's actually very important because, well, to go through this with a system of 2 equations is kind of ridiculous, right? Because it's a lot easier just to solve it by substitution. If you have a system of, say, 1,000,000 equations, then solving it by substitution is just not really feasible. But there are ways to do this matrix inversion, very simple computer algorithms, so that you can solve a system of, say, 1,000,000 equations pretty easily. So, for example, if you're trying to model how atoms react to one another, or if you're trying to model like infall of material in whatever, then you can take each individual particle and set a system of equations that defines the position or velocity or forces acting on that particle, and then you can solve that system through use of this matrix method, this matrix inversion. So it's silly to do it here with just a system of 2 or even 3 equations, but if you're dealing with a system of 1,000,000 or 1,000,000,000 equations or whatever, then you can't do that by hand. You have to do it with some sort of algorithm. All right, so here I start out with this matrix. The first one, and actually let's see, I had 0.87 here, not 0.86. I'm going to divide row 2 by 0.87. All right, so I'm doing this first number, or that first rule, and that gives me 0.5, -1, 0. And over here, I would get 0.87 divided by 0.87, which is 1, 0 divided by 0.87, which is 0, and 4 divided by 0.87, which is 4.6. All right, so already I have my value for FT2, which is 4.6, because I have that 1, 0 in the second row. All right, now I want to, I'm going to switch row 2 and row 1. So I'm just going to do 1, 0, 4.6, and 0.5, negative 1, 0. I'm going to switch those two rows. Then I'm going to replace row 2 with row 2 plus negative 1/2 of row 1. All right, and when I do that, I get 1, 0, 4.6. I add 0.5. I'm going to write it in here in longhand. 0.5 plus negative 1/2 of 1, right, which of course is equal to what? 0. And then I get negative 1 here. And then I get 0 plus negative 1/2 of 4.6, which is equal to negative 2.3. So I do that operation. Here I've combined a couple of rules. I can replace any row with the sum of that row and another, and then I'm also multiplying that row by negative 1/2. So I'm doing rules 1 and 2 at the same time. I'm multiplying row 1 by negative 1/2, and then adding that to row 2 and replacing row 2 with that. All right, so now my matrix looks like this. I have 1, 0, 4.6, 0, negative 1, negative 2.3, and just one step left to do. What is that? That's right. So I multiply row 2 by negative 1. I get my identity matrix, 1, 0, 0, 1, 4.6, 2.3. And those are my answers that we found by substitution. That's pretty cool, huh? It's actually very useful, as I said, not because it's easy to do. It's not easy to do this matrix inversion, although I think it's kind of fun. As I said, it's kind of like Sudoku, but it's useful because it allows you to expand solving just a system of a couple equations out to, X number of equations, a lot. So if we look back at our original matrix, the way we wrote them, FT2 was on the top, FWA. So we have FT2 equal 4.6, and FWA equals 2.3. All right, so on the test, you'll have a scenario where you'll have to solve a system of equations, and you'll be able to, it'll just be a 2x2 system of equations, 2 unknowns, 2 equations. And if you solve it by matrix inversion, it'll be 3 extra points on the exam. You can also solve it by substitution if you just want to check your answer. So just something, if you have extra time, you can go and do that. All right, any questions about this? You're not required to do this by any means, but it's very useful to know. It's a useful thing to know how to do. All right, let's try this clicker question. Dock worker loads crates on a ship.